So calculus rules, we're going to look at, over the next few days, several different rules to make the differentiation easier. And the first one we'll look at is quite useful, known as the chain rule. It's also known as implicit differentiation. It can be thought of as, it can also be thought of rates of change. There's all sorts of different names we give to this idea. But basically it's the chain rule. In formal language, it's this. But I don't know what that is. I never use that. I think of it as anarchy. Yeah, anarchy. You know, bring down the power. All right, it's anarchy. All right. So the chain rule you think of as anarchy because you want to overthrow the ruler, overthrow the king. So you bring down the power, but then what do? You really want to kill them, basically. So you then chuck them on the ground. So you lower the power. So bring down the power, chuck him on the ground, right? So lower that power. Right? And then, really to make sure you get him, you want to put the boot in. Well, you ever heard this term to have a bit of biff? A bit of biffo? Fighting? Well, this is a bit of diffo. Okay? A bit of diffo. Okay? So, we bring down the power, we chuck him on the ground, and we put the boot in. Right? And that's it. That's the chain rule. As I have mentioned before, it's a very strange place inside this head. Let's go back to this example we saw before. And I said, we're going to have to expand it out. What it means is I don't have to expand this out. So whenever I have some function to the power, then I can say, no, I'm going to use anarchy. Bring down the power so the 2 comes to the front. Lower the power, the 2 becomes 1, but don't forget to put the boot in. Which means differentiate inside the parentheses. We're going to kick him so hard that derivative comes bursting out of the parentheses. Okay? So we get 2 times 2. I bet you your tutors never taught you this. You had 2x plus 1 times 2. And of course I can tidy that up. Now, that is the same answer. If you have a look at what we got before, we got 8x plus 4. I've just got it in a factorised form. So we do get the same one. Why is this useful? Because now, if I get something to the power of 7, I don't want to waste time expanding the whole thing out to the power of 7. Now I can just use a bit of anarchy. Bring down the power, 7. Lower the power, 6. Put the boot in. Get that derivative out of the parentheses. The derivative is 3. 7 3s are 21. There's my answer in factorised form. So much quicker. Do another one, because it's so much fun. Especially the putting the boot in part. Oh, that's great. Bring down the power, 3. Lower the power, 2. Get that derivative out. 2x. 3 times 2x, 6x times x squared minus 10 squared. Doesn't matter if there's a number out the front, that's fine. Bring down the power, 6 5s are 30. Lower the power, 5. Bang, it's negative 2. Oh, it tried to trick me. No, the negative came out as well. So we get negative 60, 4 minus 2x to the power of 5. Where it's really useful, something like this. Because try and expand that out. X squared minus 3 to the power of a half. Little bit tricky, so I don't need to. I can use anarchy, the chain rule. Bring down the power, a half. Lower the power becomes negative a half. Kick that derivative out of the parentheses. 2x, mere mortal answer. There it is. X on the square root of x squared minus 3. So really handy for things like that with surds. The idea is basically what we call implicit differentiation. dy dx equals dy dt times the t dx. You see, they're rates. And so just like fractions, I can cancel denominators and numerators. So I can multiply derivatives together to get a new derivative. And this is what I'm really doing with this. Because what I'm saying is, hang on, this x squared minus 3, it's a bit hard to differentiate that I can't expand it out. So what I'm doing is imagining x squared minus 3 is just one thing, call it y, if you like. And I'm differentiating the y, but then I'm multiplying it by the derivative of that thing inside. Actually, I don't worry about that. I just think of anarchy and I get the answer. But once we come looking at something called parametrics later on, I don't have to recombine this to come up with the equation, because what I can now do is say, well, you're right, I'll just differentiate each little bit. I'll differentiate x with respect to t, and I'll get 4. I'll differentiate y with respect to t, and I'll get 4t. And then I can create the derivative by playing with those two. I can say, oh, well, hang on, dy dx, that would be the same as dy to t times the t dx. So 4t times a quarter, I turn dx to t upside down. And so, yeah, it's equal to t. If I wanted it in terms of x, I could then say, well, hang on, I know x is 4t, so t is x on 4. I could substitute in and I'd have the derivative in terms of x. So however I want it. More about that when we start looking at parametrics a bit later on. Okay, so 7e, which rhymes with?
70.
No, I was going to say anarchy, but anyway. All right.